So is whiteboard visible to you?
Yes, ma'am.
Is whiteboard visible to you?
Yes, ma'am.
Okay. So we have done already inner product, right?
Yes, ma'am.
Now we are doing inner product space. And then, you know, product space. A real vector space. Real vector space means having real vectors in it. A real vector space with an inner product is called inner product vector space, or can call also real inner product space also. Okay, it's called either real because it is real already, real inner product space, or simply product inner product space. Okay, so inner product we have done already. Now let us do the next topic. You got it?
Yes, ma'am.
Okay, all right.
Can you give
Now,
me an example?
sure. Just a second. The next topic related to that. In that, we'll do an example. Like example, like as previous, we have done inner space for a given vector space.
Mm.
Okay. So for that vector space which satisfy the inner product axioms is said to be inner product space. Are you getting this point?
So a vector space will have certain vectors, no, ma'am. So
Yes.
those vectors, if they satisfy the inner product axiom, then that
Yes.
vector space is called inner product space.
Yes.
So the
Okay.
vectors in the vector space that satisfy inner product axioms make the vector space called to be called inner
Inner
product
product
space.
space. Yes. Exactly.
Okay.
Got it?
Yes, ma'am.
Now the next topic is mm, distance. This is a property of inner product space. Okay.
Okay.
We are going to do properties and then we'll do, sorry, properties of inner product space. So if first we have if V is a real inner product space, then the norm or length of a vector V in vector space capital V is defined as like norm of this vector V is equal to square root of this inner product of V comma V. Okay. Means so in inner product space we can define any vector, means norm of any vector in this way. Are you getting this point?
No, ma'am, I'm not getting it. 1 minute, ma'am.
Okay.
Let me read it. V is
Sure.
a real product space. Then the norm or length of what is of a V?
Just a second. Of a vector small v in vector space, or in simply you can say v. Okay, I'm just writing
Okay.
a little bit more clear here.
Capital small
Length
V
of
and
the
capital.
vector v, you can take this as also. Okay,
Okay.
vector v, small v we are taking, which is of vector space. Then its norm can be defined as, means we are talking about the norm or length of a vector that belongs to V is defined as. Are you getting this?
Yes, ma'am.
Yeah. If you want to ask again, then I'll explain you again. Means just simple. This small vector, this small V is a vector of inner product space. Then its norm can be defined as by using this formula. Okay.
Okay.
Yes.
So basically V square. V
Yeah.
square
Yes.
under root.
Exactly. We are multiplying to itself. Yes. Okay.
Okay.
Now let us know the next property.
Okay, ma'am.
If U and V are two vectors of inner space, inner product space, sorry, then distance between two vectors can be defined as two vectors U and V can be defined as by using this symbol D between U and V, that is equal to this, we define a norm of difference of these two vectors, or it can be defined as like square root of u minus, sorry, taking this symbol, u minus v, uh, or comma, we are just multiplying them. Yes. means we are finding inner product of these.
Mm.
Are you getting? This is the formula to find distance between two vectors by using this formula.
Yeah, ma'am.
And let us know the next properties or next one is if we have a zero vector along with a non-zero, obviously we can write it as by using property of inner product, and that is equal to 0. Obviously product will be 0. You got it? Because any if any one vector is 0 vector or null vector, then we'll find the inner product is equal to 0
Yes, ma'am.
along with non-zero vector. Yes. And the next property, we have three vectors in this way. And I think we have done this property also. Additive. Do you remember?
Yes, ma'am. U V plus UW.
Yes. Similarly, we'll do for difference also. If we had minus sign between them, then we take similarly. If we have in left also, because we have done for left, now we are doing for right. So if we have u minus v along with w, then obviously we write u comma w and minus v comma w. And if we have like if any scalar is multiplied with u inner product of u and v, then we can express it as, or we can write it as also like k into u comma v. Got it?
Yes, ma'am. Let me make note of this.
And let us know the next properties. You have shared me some means material, right,
Yes,
of
ma'am.
your college.
We
This is
got
of
it.
the same topic, or it is of another one?
This is for week one. This is the topics that they shared.
Okay, chapter 2, right? I'm just checking, okay? Because
Yes, ma'am.
we have lots of means this topic is very broad. So I'm just checking which topic you have here. Okay,
Okay.
I'm just checking. Okay, vector space you have. Okay, we have done that. Give me a moment. I'm just checking and tell you.
Okay.
And okay, let's see on page number of PDF third. just below the vector space with additional structure.
Page.
Page number of, I'm just because I don't have page number of your material, but I have the page number of PDF. That is third.
Is it called matrix application?
No, no. This is for linear algebra. Linear algebra. See, we
What's the
variate
material?
map. Okay, I'm just paying. Okay, this one, because I'm going to tell you we variate mapping.
Okay.
Shall we do this?
Which vector space is additional structure? Yes, ma'am.
Because we have done vector space linearly, independent, dependent, and dimension basis also. So let us do the next. Let us do the next bivariate mapping.
Okay.
Okay. So what is it? Let us understand here. Bivariate mapping we are doing for inner product space. Okay, inner product. We are doing for inner product. See, like we are taking. Okay, I'm just telling you one by first. What is it? Let us know. Bivariate. And bivariate mapping by using the symbol we are representing. And what is it? Just we are taking domain or V cross V and to field means we'll find the result of range in field. Okay.
Okay.
Okay, so here if you
Can you
this
explain
map,
what that notation
yeah,
means? That dot colon V cross V. What does that mean?
this representing inner product.
Okay. Yeah. The first one is inner product. The second
Yes.
one is
No, this symbol represent us inner product.
okay. And what is that colon V cross V?
Do you remember function?
The domain
Function.
is the input, range is the output.
Yes. So this is domain.
Okay. By
Means we'll have domain from V cross V and range in it field. Okay. Scalar set of scalar. Now got it?
yes. Ah,
When we say this mapping is V-variate is defined to be inner product if it is satisfy the following properties, or you can say following axioms. Okay. This is defined, means this mapping, this bivariate mapping is said to be inner product. Okay, when it is satisfy the following properties. And let us now learn the given properties.
1 minute, ma'am. Just give me a minute.
Yeah, sure. Okay, I'm just writing an next page. Okay, meanwhile I'm writing. Shall we continue?
Yes, ma'am.
Okay. So this bivariate mapping, like this mapping for this inner product, okay, defined as this. So when we can define its inner product, then it will satisfy the following properties or following axioms. Okay, what are these? Let us know. If two vectors, or we are taking a vector, this inner product space, and one scalar alpha you can say it, or they are taking a, so you can, that is why I was asking you for your material, because different books use different symbols. Most probably they use v for vector space, but for scalar sometimes they use alpha, and some in book they use cd, and in your book now they are using a. So let us take, we will take a scalar and two vectors. Now we need to satisfy these three properties. Let us know them. First is, if we have like this scalar product with the u and having in this way plus w and comma v is equal to have a and u comma v plus v comma sorry, w comma v. Okay, just a second. Okay, if this like we are multiplying a with u, and which let us add it to w and comma v, and which if it can be defined as, okay, this is property, okay, if it can be defined in this form, then we can say it is linear in first argument. Okay, then we say it is linear in first argument. You got it?
Yes, ma'am.
And we can verify with by taking two examples also, as we have done in previous class. You can take that u and v also to verify each and every. Okay,
Okay.
and it is, if you have any doubt then you can ask me again, I'll explain you. It is linear, means just like a formula type. Okay, when like you need to prove linear uh, in its first argument, then use this property. Okay, in somewhere you need to prove it in its first argument. Next, if we have u, inner product of u and v can be represented as having v comma u, it is satisfied congruent, like bar represent congruent. Do you remember that? This bar,
Oh,
so
okay.
yeah, conjugate, sorry,
Oh, okay.
bar represent conjugate
What's
always.
conjugate?
Like if we have, do you remember iota?
Iota.
This symbol, do you remember?
Necessary component.
Yeah. So if we take opposite sign of that, that is component, that is conjugate of iota. Okay.
Okay.
Yeah. Value of iota is, do you remember iota is equal to square root of -1?
Yes, ma'am. Yes, ma'am.
Yes. So if we have this form, means inner product can be expressed as a product, means just
Conjugate.
yeah, by taking the conjugate of that. then it is said to be, or it is satisfied a conjugate symmetry. Conjugate symmetry. We have done already this property. Still, let us do once more. U inner product of u and v will always greater than 0 for all. Sorry, u comma u, not for v. Now here we are taking the same, means we are just multiplying with itself for
Yes.
all u belongs to vector space V. Okay, this is positive definite. Okay, because we cannot, why we cannot take two different vectors, because sometime obviously we can have negative symbol also, like for example if we have vectors 1 2 3 and have like a -10, -2 and something else, when we multiply, uh, then obviously we'll get negative result. So if we multiply positive or negative any vector, then we'll definitely will get positive result.
Yes.
Obviously when
Since
we multiply having negative sign, yes,
yes,
obviously we are
since
multiplying with itself,
time
so obviously, yeah,
u with
yes,
itself, we're going to be taking square, and square will always be greater than
yes,
0 unless u is 0.
yes, yes, exactly. Okay,
Okay.
so now let us do the
And
next.
what is this
What was it?
conjugate symmetry? Can you give me an example?
Sure, sure, I'm giving you. So conjugate, like if we have z, like any complex number, I'll make you remember this. So
I mean,
conjugate
the
of z
property.
is,
Can you explain the
yes,
property itself, ma'am?
this conjugate
Like with
symmetry. Yes, sure, sure. Just a moment. I'm taking a few examples. Like take vector like 2 having element 2 and 3 iota 4, and we have like 2 4 and minus 2 iota. So let us multiply them to find inner product. 2 3 iota and 4. I'm just multiplying with 2, 4 minus 2 iota.
Ma'am,
Then,
so it has to be complex number.
yeah,
Why?
because for conjugate, to show conjugate, okay? Hello?
Yeah, I understand that for conjugate it has to be complex, but this bivariate mapping is of inner product of
Yeah,
a vector space, right?
yeah,
So in the vector space, it can either be real or complex, no ma'am. So why is
yeah,
it?
yeah. Actually, if we take only real values, then we say the real, okay?
I'm
Are you
actually
getting
not
this point?
understanding the bivariate mapping concept then.
Okay, I'm explaining you, okay? Uh, Give me a moment. I'm just looking your material first. Okay, so you don't have a question in this met. Okay, okay. See below, see below of just this definition remark. For a
Hmm.
real vector space, we take f is equal to r. Just scalar is equal to real number because we are not including here iota. Okay. So obviously this symbol obviously just follow the commutative which we have done because we are not including here this that imaginary part. Are you getting this point?
No, ma'am.
Okay, I'm telling you. See,
Okay.
see, definition is that if we are doing for real, okay, then we say this a real product, inner product space, okay.
Okay.
And here for conjugate, we must have that to show that complex form. But if we are doing for only real part, so just z is equal to will take only real like that. Okay, we just ignore this part. Okay, for real one.
Okay.
Yeah.
Okay, that line, it's just symmetry for real numbers, but
Yes.
for complex field, then it is
Yes.
conjugate symmetry.
Yes. And here that is why this can we are representing this. This will also, you know, just we have done the just symmetry property. We are using here only symmetry because so
Hmm.
we here we don't have any like that imaginary part. We are taking only real one. Okay, so this also for this for real, I'm telling you, for real vector space, obviously this inner product v comma u bar is equal to also v comma u. Okay, are you getting this point?
Yes.
Because obviously we have real part only, we don't have any and including any iota. Okay,
For
that is why
real,
obviously
UV is equal to VU, but for
yes.
complex, UV is equal to conjugate of VU.
Yes. So here we are now conjugate also is equal to that. Okay, that is equal to inner product because obviously we don't have here iota form. That is
Okay.
why we can express this conjugate. simply in this form for real vector space. Okay.
Okay.
And for all, obviously we'll have that if they'll tell you about. And if we consider only real, then obviously we'll do that. We'll take this is equal to inner product of V and U. Are you getting this point now?
Yes, ma'am.
Okay. And so now let us see the next definition. 2.1.8.
Okay.
Shall I read in this or okay? Give me 1 minute. I'm just sharing you. Okay, on screen. Then shall I explain you on screen?
Okay, ma'am.
Okay, because we can save the time if you want by doing this way. Otherwise, I'll explain you each and every topic on this whiteboard also. But you have your own material. That is what I'm saying to you. Just a second. Give me a moment. Whenever we need it, and then we will do on whiteboard.
Yes, ma'am. I'll write it down.
Okay, sure. Okay, so definition 2.1.8, consider the vector space V, and they are denoting this vector space by nu, this symbol nu, not a V. And V variate mapping is defined as F V cross V to F. Suppose F is conjugate and symmetric and then linear in at least in first argument, then mapping F is defined as. Okay.
Okay.
Means if we have F is conjugate if we have. Then we have these properties. Positive definite of F U means having inner product of U and U with itself will be greater than 0. And here U belongs to this V. Just leaving the null vector. Okay. Just they are taking then by using this symbol like V and using this symbol means we are not including here null vector. Got it?
Okay.
Similarly, for second term also negative definite we can define as function or it is mapping of inner product of U with itself is less than 0, then we still U belongs to the same thing. We are not taking null vector or 0. Okay. And a positive semi-definite or non-negative definite we can define as mean positive semi-definite means it is also greater than and equal to 0, and still we are not taking a 0 null vector here. And for negative semi-definite or non-positive definite we are taking just less than or equal to means for semi-definite for definite we take just greater or less. Okay. And for semi we are taking less or equal, either greater or equal, both
Okay.
symbol together. Okay.
Okay.
Are
But
you getting me? Yeah, sir.
I'm getting this. But then, how will it be that a vector into a vector
Yeah.
gives you a value less than zero? I mean, a vector into itself will give only positive value, no ma'am. How is it giving a negative value?
Okay, I'm telling you. See. Uh,
Or even giving you zero or less than or equal to zero?
okay, just a second. Let us.
Because they're saying f of
Actually, listen. Because they are taking this mapping. Okay, they are taking the mapping. They are talking about mapping, not inner product. They are talking about mapping of that inner product. Okay, so these
uh,
are the properties for the mapping, not for only inner product.
okay, so it can be any function.
Yes, exactly.
Okay, so any function can be called negative definite if
Yeah,
the value that it maps to the field is negative.
yeah.
Okay.
Okay. Yeah. And see the
Okay.
below recall. Yeah,
Minus
tell.
u. Okay.
Yeah, I'm not getting it. Can you repeat it, please?
Since they're saying it's just a function,
Yes,
then and they're not saying it's inner product. So
saying for function of that inner product. Function of that inner product. They are talking about.
ma'am, inner product will always be greater than zero, right?
Yes, exactly. For
Uh,
example, if we have, you know, like this, having negative sign, or we can define it as like u plus one, or anything else, or just by taking in this form. So
hmm.
obviously we'll take then a negative. Okay. Still you have product, like for example you have product 10, inner product 10. Then we put here, obviously you will get minus 10. Okay.
Yes,
For example, as we take means like x is positive, even x square is also positive. If we have like this, obviously we'll have the negative. Got it?
got it.
That is why here we are talking about for mapping or for function. Okay.
Okay.
Yes. And you can see here the complex number z is equal to a plus iota b, just below recall, for recall, and complex conjugate we have. But for real vector space, we are not taking this. We are just taking the real part. Okay. But
Hmm.
if we need to find the conjugate, obviously we need to take opposite sign of iota.
Okay.
Okay. Yes. So the next, let's see the next definition. That is 2.1.9. Consider the inner product space. Here we are using vector space, in new. And inner product along with, inner product, we take vector space along with inner product. The inner product norm of vector V that belongs to V can be defined as, we can also refer to its length, and it is denoted by norm of V. Okay, and norm of V belongs to real number. Obviously we'll get a means after simplification we'll get a value, and that belongs to obviously a real number. Are you
Okay.
getting this
Yes.
thing? Yeah.
Yes, ma'am. This is what you already taught me.
Yeah. Yes, we have done this already. And see the next one, this on page, next page. See this. So when we first note that in inner product, with inner product norm, the following relationship is satisfied. Sometimes we need to use this relationship to solve the questions. This one,
Okay.
we have here inner product of u and v over norm of u and norm of v is always greater than or equal to minus 1 and or less than equal to 1.
Okay.
Okay. So let us see the next definition, 2.1.10. Consider the inner product space new having the inner product along with the angle between vectors u and v which belong to v is denoted by theta, and it always obviously belongs to 0 between 0 and pi, and can be defined as theta is equal to cos inverse and inner product u and v over inner product, norm of u into norm of v.
Okay.
Yeah. So by this definition, we can find the angle between two vectors.
Okay.
Okay. Yeah. So shall we do this by using an example?
Okay, ma'am.
Okay. Like if you have vector u is equal to vector u is equal to like or 2 4 and we having 1 3, and we need to find angle between these two vectors. So formula is, just let us find theta is equal to cos inverse inner product of u and v, and just over norm of u into norm of v. Hello, can you hear me?
Yes, ma'am.
Okay, so first of all, just find this inner product. So 2 into 1 plus 4 into 3, and we have 14. Now let us find norm of u, that is equal to just inner product of uh, this u with itself, and that will be 2 with 2 plus 4 with 4. Are you getting this point?
I'm also solving, ma'am. Just give me 1 minute.
Okay, sure. That's good.
Ma'am, so I got cos inverse of 7 root 2 by 10.
Okay, so here we have 14 and you have root 20 into root 10.
Yes.
So, okay, so cos inverse, you have 14 and you'll have 10 outside and here root 2. Are you getting this?
Yes, ma'am.
Okay, so what you got?
I got cos inverse, same thing, 14 by
Okay,
root 10 into root 20. So then I got 14 by 10 root 2.
yes, and we can
Then
reduce it. Okay,
then I did cos inverse on calculator and got 8.13.
okay, okay. You can just leave by simplifying in this form. Okay,
Okay, ma'am. So this is
so
the
in this
angle
way,
between these two vectors in the vector
yes,
space V.
yes, exactly.
Nice, very nice.
Okay. So, so
Ma'am,
tomorrow you will do exercise?
tomorrow no, ma'am.
Okay, okay, okay. Yeah, you told me. Okay, all right.
Thank you.